Hi folks, welcome to 7.6. This is going to be the last section on the next exam, and we're going to finish off here with de Moivre's theorem and the nth root of complex numbers. So let's go back a little bit to the last section, the last two sections, and talk about what we know. So we know that if we have a number, and this number is in a polar form, okay, we could write it like this. And again, that comes from our z equals a plus bi, all right? And so just as a reminder, we find our r by finding the square root of a squared plus b squared, and we find our theta by finding the inverse tangent of b over a. Now we're going to need these formulas even in this next section. They'll help us convert when we need to convert into this form. And in the last video, we also talked about two other formulas, one for the product and one for the quotient. So we've got our product here and our quotient formula here. All right, so we're going to go ahead and add on to this in this section. So here's what's new. If we want to find the powers of complex numbers, okay, we want to find the powers of complex numbers, then we're going to use the following formula. If I have z to the n power, then I can write it like this. R to the n times cosine of n theta plus I sine n theta. We could also write this as r to the n times cis n theta. The other new thing we're going to learn in this section is how to find roots of complex numbers, so sort of the opposite of powers. We're going to try and find roots, and we can find this using one of two formulas. One of them is going to be for when we use radians. Okay, so the top formula is what we want to use if we're looking at radians. And then if we want to use degrees, we're going to use this bottom version of the formula. Okay? So we're going to go ahead and start with our powers of complex numbers. We're going to do a couple examples, and then we'll go ahead and find the roots of complex numbers and do a couple examples there. So, powers of complex numbers. That's what is meant by de Moivre's theorem. So de Moivre's theorem allows us to use a shortcut to evaluate expressions such as the one below. So let's take a look at example number 1. It says evaluate the expression 1 plus I to the 5th power. So in order to do this, we're going to go ahead and start by converting to polar or trig form. And that's where we're going to need to find our r and our theta. So r equals the square root of 1 squared plus 1 squared, which leaves us with the square root of 2. And our theta equals the inverse tangent of 1 over 1, or the inverse tangent of 1, or we can say that that is pi over 4 radians. That means we can convert this expression, z, into root 2 cis pi over 4. So that's our first step. We're going to convert those numbers. The second step is now we're going to apply the formula from above. So step 2, apply formula. And so we have z to the 5th power. That is the same as saying square root of 2 cis pi over 4 to the 5th power. Now, according to the formula, this is going to be the same as raising r to the power we want, and then taking cis of that power times my theta. So, now that we have this, let's go ahead and simplify. 2 root 2 to the 5th is the same as root 2 times root 2 times root 2 times root 2 times root 2, and cis of 5 pi over 4. Now let's clean up this front end. Root 2 times root 2 will make 2. Root 2 times root 2 will make 2, and then we have 1 left over. So that's going to leave us with 4 root 2 cis 5 pi over 4. Now to finish our question, because we started in rectangular form, we need to convert back to rectangular form. So that's going to be our third step. We're going to convert to rectangular form. So that all we need to do for that is we're going to expand. So 4 root 2 cosine of 5 pi over 4 plus I sine 5 pi over 4. And that equals 4 root 2, let's see, cosine of 5 pi over 4 is negative root 2 over 2 plus I, and sine of 5 pi over 4 is also negative root 2 over 2. And when I continue simplifying this, I'm going to end up with negative 4 minus 4i. All right, so that's a good example of how to work through using de Moivre's theorem. So step 1, you're going to convert to polar or trig form. Step 2, you're going to apply the formula. And step 3, you're going to convert to rectangular form. All right, let's do one more example here. So example 2 says evaluate the expression root 3 plus I to the 7th power. So we're going to follow these same few steps. First one, we're going to convert to polar or trig form. Okay? And so we have to find our r, which is going to be the square root of the square root of 3 squared plus 1 squared. And that will give me the square root of 4, which will give me 2. And then to find my theta, I want to do the inverse tan of 1 over root 3. And if I look at my unit circle, that's going to come from pi over 6. All right, step 2, we are going to apply the formula. So z to the 7th is going to equal r to the 7th cis 7 theta, which is going to be 2 to the 7th cis 7 pi over 6. Now, our last step is to convert it back to rectangular form. So convert to rectangular form. Okay, so that just means we need to expand it. So 2 to the 7th times cosine of 7 pi over 6 plus I sine 7 pi over 6, and that's going to equal 2 to the 7th times, let's see, this will be negative root 3 over 2 plus I times negative 1/2. All right, so from these questions, you can probably tell that it's really important that you know how to work with that unit circle pretty fluently, okay? Now, when we clean this up, we will end up with a negative 64 root 3 minus 64i. And that will be our expression evaluated as we raised something to the 7th power. Certainly, this is a lot better than foiling something out 7 times, or in this case, foiling it out 5 times. And this is really helpful when those powers get larger, like 10, 20, 30, 40, 100. Okay? So we're going to stop here. When we come back, we're going to talk about roots of complex numbers and how to find those. See you back here.